Now consider two orthonormal bases. One is chi n and one is un in the same vector space V. They are both orthonormal bases. It means we can write chi n as sum w mn m un. We can write the vectors of one orthonormal basis as a superposition of the other normal basis. Now, since this is an orthonormal basis, then chi k chi n should be delta kn. That's the definition of orthonormal basis. If we substitute this expression for chi n, we get sum over m1, sum over m2, w star, w are complex numbers, so m1 k w m2 n u m1 u m2. Since um is also a orthonormal basis, so this is delta of m1 m2, so we can replace all m1 with m2 when we sum over m2 and we just call it m, so we get sum over m wmk star wmn and delta n. So this has to be equal to delta kn. Now let us see what it looks like. Sum over m, we have w dagger km w mn. Now you can see that w dagger is actually the w star and transpose if we have matrix w, and so it means w ij element of this matrix w, the w dagger's ij element will be w star ji. So this is what we have done here. W star mk becomes w dagger km, km element of w dagger matrix. So it means chi k chi n becomes sum over m w dagger w. You can check that this is actually the matrix multiplication of w dagger and w and the kn element of that, and this is equal to delta kn. This implies that w dagger w is identity. Similarly, we could have written u in terms of chi and we would have gotten w dagger equals identity. This implies that w is unitary. So from here we can conclude that a unitary operator causes a basis transformation. And when we say basis, we mean orthonormal basis. Okay, so unitary transformation, a unitary operator, takes one orthonormal basis and map it to another orthonormal basis. So this is what we showed just now. But we can do something else also. Let us say we have z, which is chi n un and sum over n. Now if z acts on um, it will give us chi m. This is also a transformation from one basis to another. Okay, so we can see what is z dagger, that will be sum over n chi n un sum over m chi n, and when we multiply sum over nm um will give us delta nm chi m delta nm, which is equal to sum over n chi n, which is identity. Similarly, z dagger z is also identity. So this is also a unitary. So now this is another example of unitary, which is taking one orthonormal basis to another orthonormal basis. So can we find a relation between the two unitary? So this can be one assignment problem. This will be a fun problem, not very complicated, but not really straightforward. So I will recommend everyone to try this thing and try to figure out what is the relation between Z and W. Okay. So with this, we have covered all the important classes of operators, but there are some operators which we will encounter eventually, which will come at a little later stage of our course. Positive definite and positive semi-definite operators. So if an operator A, if we take the inner product of psi with A psi, and this sometimes is called expectation value also. So if the expectation value of an operator A is always positive, then it's called positive definite operator. This should be true for all psi in the vector space B. Okay. If this is true, then it's called positive definite. If it can be 0 and positive, then it's called positive semi-definite. And any Hermitian operator with positive eigenvalues are positive definite operators, and Hermitian operator with positive and 0 eigenvalues are positive semi-definite operators. So this was one class which we will be using time and again when we talk about the states and density matrices. Now there are some interesting expressions and representations of operators, the various operators we just discussed. So we will be discussing that. So consider an operator A acting on, so the eigenvalue equation, the characteristic equation of an operator, and for a Hermitian operator, like A is a Hermitian operator. Now let us define a matrix S which is made by using the eigenvectors of the operator A in the following way. We put first column as the first eigenvector, second column as the second eigenvector, and nth column as the nth eigenvector. In that way, we are assuming the matrix A was n by n, so the vector psi n will be also n-dimensional vector, and there are n of them. So S is a n by n matrix. Let me repeat, we stack the eigenvectors of operator A, Hermitian operator A, as the columns of matrix S, and hence we get a n by n matrix. Now interesting thing about S is, first of all, let us see what is S dagger. S dagger will be psi 1, psi 2, psi 3 and psi n. Now what is S dagger? S dagger, that will be psi 1, psi 2, psi n times psi 1, psi 2, psi n. There is no trick I am using here. You can put the vectors, you can take the explicit form of vector, you can put them, and you will see this is a valid matrix multiplication. Then when we multiply, it will be the first element of the vector. This is the, we can treat this thing as the vector of vectors. and this is as a column of vectors. So this is a row of vectors, this is a column of vectors. So the first element here and first element here, we multiply second, and we add all of the elements. So it becomes sum over n, psi n, psi n. So S dagger is sum over n, psi n, psi n. Since psi n are the eigenvectors of a Hermitian operator, so they form an orthonormal basis and they form a complete basis. It means sum over n, psi n, psi n. This must be identity. Now let us try S dagger S. That will be psi 1, psi 2, psi n, psi 1, psi 2, psi n. This will be matrix. The first element here will be psi 1, psi 1, psi 1, psi 2, and so on, psi 2, psi 1, and so on up to psi n, psi n. Now psi's are orthonormal, so only the diagonal element will be 1, everything else will be 0. So matrix will be 1, 1, 1, 1, and so on, and 0 everywhere else, which means identity. So from here we can see that S dagger equals S equals identity. So somehow the matrix S turned out to be unitary. What we have done is we have taken a Hermitian operator A is Hermitian, and we have eigenvectors of it and we have eigenvalues of it. We make a matrix S out of the eigenvectors of A, and we see that this matrix S turns out to be a unitary matrix. So now let us simplify the equation. We get A S, which is A acting on psi 1, psi 2, psi 3, psi n, which is, if we do the calculation, it will be A psi 1, A psi 2, A psi n, which will be lambda 1 psi 1, lambda 2 psi 2, lambda n psi n, which will be psi 1, psi 2, psi n times lambda 1, lambda 2, lambda n, where everywhere else it is 0. So we have seen that, and this we can write as the same matrix S and this diagonal matrix D. So we have seen that AS equals SD. Okay. So we have written the whole eigenvalue equation in this matrix equation. Now, since S is unitary, we can multiply with S dagger. S dagger is identity, so we get A equals S D S dagger. Hence, any Hermitian operator A can be diagonalized using a unitary operator S. So this is very simple and intuitive proof that any Hermitian operator can be diagonalized using a Hermitian operator S. Not just that, anti-Hermitian can also be done that, because anti-Hermitian is just I times Hermitian. So the proof goes in a similar way. And for other operators also, we can do whatever is related to Hermitian operator. Now, what will happen if A was not a Hermitian operator? If A is not a Hermitian operator, then psi n are not orthonormal. Not orthonormal. But let us assume that but we have n number of linearly independent vectors psi n. Then S, which is psi 1, psi n. This is a matrix of n linearly independent columns. If you remember our linear algebra from our 12th standard, if we have matrix with n linearly independent vectors, then the S inverse, the inverse of the matrix exists. So it means AS equals SD, that did not require any information about the unitary of S, unitarity of S. So here if we multiply with S inverse, we get SD S inverse, and we get A equals SD S inverse. This is the diagonalization of by similarity transformation. It's called diagonalization by similarity transformation. The previous one with unitary, that is also similarity transformation, but of a very specific type, that we are using the unitary matrix instead of invertible matrix, instead of just invertible matrix. So there are two problems, two assignment problems we can think of right now, that if you have two Hermitian operators, self-adjoint operator A and B, such that they have same eigenvectors, then they commute. That is, A, B equals 0. Okay, prove this thing. This is an assignment problem. If A and B have the same eigenvalues, then they are related by a unitary transformation. So these are the two assignment problems one should try, and they will be very intuitive, very interesting to understand. Now we will discuss functions of operators. We will be mostly concerned with either Hermitian or anti-Hermitian or unitary operators, but if we have an operator A, which is S, D, S dagger, like we have seen, then A square will be S, D, S dagger times S, D, S dagger, which is S, D square, S dagger. If we extend this thing, if we have a function of A, any function of A, then it will be S, the same function of D, S dagger. Okay, so this we can see by like one example we can consider, which is the exponential of A. The exponential of A will be written as identity plus A square over 2 factorial and so on. And we can write A S D S dagger plus S D square over 2 factorial S dagger plus and so on. And this identity is also S dagger. This is S identity plus D square over 2 factorial and so on S dagger. And this is S exponential of D S dagger. How is it useful? It's useful because calculating directly exponential of A is difficult, but exponential of a diagonal matrix, which is exponential of lambda 1, lambda 2, lambda n, is nothing but exponential of lambda 1, exponential of lambda 2, exponential of lambda n. So this part is trivial to calculate, and then we have to just multiply it with the unitary matrix, and we get the function of the operator. Now let us say we have a matrix M, which is exponential of A, And let us say this is unitary. Then m dagger equals m inverse. M dagger can be written as exponential of a dagger, and m inverse is exponential of minus a. This implies that a dagger has to be minus a. And by definition, a dagger equals minus a implies that a is anti-Hermitian. Or a can be written as IH, where H is Hermitian. This implies that any unitary operator m can be written as exponential of IH, where H is Hermitian and m is unitary. Now there can be an assignment problem, which let's call it 3. If we have unitary operator m, the eigenvalues of m will be pure phases. That is exponential of I theta, that kind of form it will have. Okay, and eigenvectors will be orthonormal basis. You have to prove this thing. And fourth assignment problem can be, let us say we have m1 which is exponential of IH1, m2 which is exponential of IH2, then m which is m1, m2. You can see that if m1 and m2 both are unitary, then m which is the product of m1 and m2, this will also be unitary. And this can also be written as exponential of IH. Find H.